This is a brief account of the Henderson equation, fundamental to the understanding of acid-base physiology. Let's begin by reviewing the definition of an acid, base, and a buffer. And before I begin, let me apologize for any hesitancy and flubs. This is my first attempt at making a video like this, and so please bear with me and pardon any imperfections. An acid is defined as a proton donor. It's a molecule or ion that can donate protons in aqueous solution, whereas a base is a proton acceptor, and a buffer is a substance that can reversibly accept or donate protons. And while we're talking of bases, I'll be using the term base and alkali synonymously in this presentation. Let's consider the major body buffer systems. These are the bicarbonate system, proteins, and the phosphate system. The most important is the bicarbonate system because it is an open system and the lungs can dispose of excess carbon dioxide. The protein system is almost as important, and the major protein involved is hemoglobin with inside erythrocytes. The phosphate system is less important, but nevertheless does play a role. Let's concentrate on the bicarbonate system, the major buffer system. And I have to apologize at this stage. Microsoft Equation Editor totally defeated me, and I've had to resort to pen and paper. But the equation that we're concerned with is this simple one. Carbon dioxide dissolves in water and slowly, spontaneously, or rapidly under the action of carbonic anhydrase is converted to carbonic acid, which can dissociate into hydrogen ions or protons and bicarbonate ions. By the law of mass action at equilibrium, we can define an equilibrium constant K, which is equal to the product of the hydrogen ion and the bicarbonate ion concentrations divided by the concentration of carbonic acid. And the concentration of carbonic acid in turn is given by the product of solubility of CO2 in aqueous solution and the partial pressure of CO2. And the solubility coefficient in molar terms is 0.03. We can wrap the 0.03 and the K into one constant and come up with this equation, which can be rearranged to give the simple Henderson equation. The hydrogen ion concentration equals 24 times the PCO2 divided by the bicarbonate concentration. Let me put this up front and center so that you can let it permeate into your consciousness and memory, because it's an important equation. Now, just a year or two before Henderson devised this equation at Tufts University, Sørensen, working appropriately in the Carlsberg Brewery in Copenhagen, had devised the concept of pH. And so almost immediately, Hasselbalch gleefully took the Henderson equation and, to complicate the lives of generations of medical students since, he took logarithms to both sides of this equation, multiplied the result by -1, and came up with the Henderson-Hasselbalch equation shown at the bottom of this slide. The information in the Henderson equation and in the Henderson-Hasselbalch equation is exactly the same, and you can use either equation for converting between the various components of the bicarbonate buffer system, just depending on whether you prefer to work with a linear equation or a perverse negative inverse logarithmic one. Let's return to the Henderson equation, but before that we have to be able to convert easily between pH and hydrogen ion concentration over the range that might be encountered in serum. As we've just seen, the normal hydrogen ion concentration is about 40 nanomoles per litre, which corresponds exactly to a pH of 7.40. And close to the normal hydrogen ion concentration, hydrogen ion changes 10 millimoles per litre up for every change of 0.1 pH down. Once you get beyond about 0.1 or 0.15 pH units away from the usual value, this relationship breaks down. But there are some easily remembered lodestars in the current political terminology. A pH of 7 corresponds to a hydrogen ion concentration of 100, pH of 7.1 is 80, and a pH of 7.7 is 20. And so if you're not close to normal pH, you can get a pretty close approximation by interpolating linearly between these values. Now, coming back to the Henderson equation, if we put in the normal values for these reactants, you can see there's a pleasing symmetry. The normal hydrogen ion concentration is 40 nanomoles per litre, which is equal to 24, our constant, times 40 millimeters of mercury, the normal PCO2, divided by 24 millimoles per litre, the normal bicarbonate concentration. Note that the concentration of hydrogen ions in nanomoles per litre is about 1,000,000 times lower than the concentration of bicarbonate ions, which is expressed here in millimoles per litre. But this symmetry of these values obviously computes in the equation and helps you to remember the relative magnitude of these numbers. Normal hydrogen ion concentration of 40 nanomoles per litre, PCO2 of 40 millimeters of mercury, and a bicarbonate concentration of 24. The other way in which the Henderson equation is helpful to you is to recall that the lungs control PCO2 and the kidneys control bicarbonate. So we can crudely parody this equation as the hydrogen ion concentration is proportional to the action of the lungs over the action of the kidneys. If the lungs work harder, that is to say increase alveolar ventilation, then PCO2 will fall and the hydrogen ion concentration will fall, the blood will become more alkaline, a respiratory alkalemia. If the kidneys fail to maintain the bicarbonate concentration so that it falls, the hydrogen ion concentration will increase, a metabolic acidosis. If the kidneys reclaim a lot of bicarbonate and return it to the blood such that the serum bicarbonate level rises above normal, then the hydrogen ion concentration will fall and we'll be dealing with a metabolic alkalemia. So the take-home point is the simple Henderson equation. Hydrogen ion concentration is 24 times the PCO2 divided by the concentration of bicarbonate. And I thank you for your attention in listening to this video.